Anyway, so some chemist who is very familiar with the solubility guidelines or rules recognizes that, hey, wait a minute, I know that I can get the calcium to precipitate out by adding some oxalate ion. So what they did, and I don't even know if the question even stated, doesn't even say what compound was used to bring the oxalate ion to the table. So what do you think a compound might be, an appropriate compound to bring the oxalate ion into this equation?
Is it water? Carbon dioxide?
None of the above. A compound that could bring the oxalate ion to the reaction. Something that will have a spectator ion that does not participate in the reaction. How am I going to get the oxalate? So here we go. We have this container. I know, you finally got it. That's okay. So we've got this container. We've got this little rock sitting in there. That rock has the three components that we were talking about. Hydroxide, calcium, what did you say, phosphate? Okay. It has all of these things in it. We want to isolate just the calcium. And probably some impurities are in there too, some other things. Okay, it's a rock. Okay. And so we want to isolate just the calcium. We're going to put this possibly in some water. How can we get, what compound can we add that brings the oxalate ion in to get this to react?
I don't know. Sodium oxalate?
Say sodium oxalate? How are we going to get the, remember, ions can't exist by themselves, but it's saying that we're going to add oxalate ion. Do you see where I'm going with that? The question's saying we're adding oxalate ion. Well, you can't just add oxalate ion. That doesn't exist by itself. It has to be associated with some sort of a positively charged ion. So I'm just asking you, not that you have to know this for the question, I'm just trying to have you use your brain a little bit, what compound would be a possible one I could throw in? Joe suggested sodium oxalate. Why sodium oxalate? Why would that be a good one?
Because it can dissociate.
Well, one, it completely dissociates, and what is the sodium going to react with? Nothing in here, because remember, sodium is a group 1A metal, and it doesn't completely dissociate, so that's not going to cause anything else to precipitate. You see where I'm going with that? It's not going to cause the phosphate to precipitate. It's not going to cause the hydroxide ion to precipitate. But the oxalate ion will react with the calcium ion to form a precipitate that we can collect, and as it says, dry. Are you guys following? So, what was the mass of the calcium oxalate that was precipitated out? 2920. Okay. Say this again? Okay. Is that right? We good?
Yeah, I was just confused because it's like with water, but the water
Right.
might
Okay. So the calcium, say for example, we'll say sodium oxalate was added. Okay. Obviously, the sodium ion stays in solution. The oxalate ion selectively precipitated the calcium ion. There's a phrase that you're going to either read if you haven't encountered that yet or see it in some of the questions that we're going to have. Selectively precipitated the calcium out as calcium oxalate. We now know the mass of the calcium oxalate. If we know the mass of the calcium oxalate, can I find out what the mass of calcium was that was in that? This is an incredibly familiar process. If you remember our combustion analysis problems, where we were able to find the amount of carbon that was in carbon dioxide and the amount of hydrogen that was in water. Do you guys remember doing that? And then where did the carbon and the hydrogen come from? From the original compound. Well, this time we're looking for the calcium that we precipitated out, reacted, and we have a product. Where did that calcium come from? The original sample. It's exactly like a combustion analysis problem. The process is exactly like it. Yes, Gracie?
So the rock is just a combination of phosphate,
Of these things and some other...
Don't we have to know the other things too?
No, because we only, in this particular case, we only care about the calcium.
But wouldn't the mass be affected? Like, wouldn't a
The mass of calcium? No.
Oh, it's percent by mass, not the mass.
There we go. Here we go. And there. How am I going to find the mass of the calcium?
Like not the formula mass, but...
No, you're exactly right. The formula mass of what?
The calcium.
Well, okay, what is the mass of calcium? Anyone? 40.08.
And then over the formula mass of calcium.
Calcium oxalate.
128.10.
Okay? Because remember, what this represents is the percent by mass of calcium in calcium oxalate, which we can then multiply by the mass of the amount of stuff that we actually have. We've been doing this since approximately the second or third week of the class, a little bit of it. Okay? And so now what are we going to be left with? Mass of calcium, when it's all said and done, right, when everything cancels out. And to find the percent that was in the rock, what are we going to do? Divide it by the mass of the rock. And we're going to get our percent. Yes. Well, we're doing a percent, so is that what you mean?
Like, no, you know how you always tell us you have our
Yeah.
in terms of, like, what...
Yeah, I understand what you're saying. What is our result? We don't care about the rock.
But, like, there's no, like, point when you say how you know what
Oh, you mean like, oh, I see what you're saying. Are you saying that? There you go. It would probably be a good, I'm going to highly doubt that you're going to, on the AP exam, if you'll be, no, I know, it's a fair question. Where I'm going with this is, I should have put that up there so that everyone's clear on what that mass represented. So it was my fault for not putting that up there. Yes?
I understand the math part. I just don't understand that, like, the first part of, like, how it's working. Does that make, like, I don't understand, is the 0.4367 gram sample of the
rock. So I'm telling you, you go out in the field and find this rock.
That's the mass of the rock.
Yeah.
And it's saying find
in that rock.
How much calcium is there?
Is in that rock.
And it's telling you that you were able to precipitate 100%
yes.
of the calcium out of
yes. Right.
And then we just use the ratio
yeah.
to find what was in there, and then that goes to the total.
Right. If you're ever presented one of these questions, you won't have to have the entire thought process and discussion that we have had. I just wanted to kind of let you think this question wasn't just like made up. This could be something that would be actually done. As some of you are actually going to, weren't some of you wanting to go into forensics or something like that? I know, or a couple of you were, right? So these are types of things that you would do is say, okay, well, let me tell you this. Before any of this happened, somebody had to take this rock and find out what was actually in it by some other means. Okay? Now, we could do a flame. You guys remember flame test? Okay? Calcium had a really distinctive reddish-orange glow. You burn this stuff or heat this stuff in a flame, you get that reddish, orangish glow. Hey, there's calcium in here. We don't know how much, but we know it's in there. By other means, you can find out if there's phosphate, if there's hydroxide. So that's the first thing you do is find out, hey, what's in this stuff? There's your forensic thing, right? Then, if you want to find out how much there is in it, you could, in this case, knowing that calcium oxalate is going to be an insoluble product, you could add some oxalate ion to precipitate out the calcium, and then find out how much calcium there was. Yes? Precipitate. All right. And again, I'm trying to relate it to what you would do. You're not going to have this entire thinking process when you do one of these problems. I just kind of want the problems all come down to almost exactly this every time. You just have to figure out what information to put into that. You know, you're going to have a total mass of the sample. You're going to have something that got precipitated out because it is gravimetric analysis, and you're going to have to find the piece, the amount of the piece it is that you're looking for out of that precipitate. That's what these questions come down to. They'll put them in such a way that it makes it kind of confusing what's what. I'm just trying to get you to relax a little bit and just focus on the things that you care about. We don't care about the phosphate. We don't care about the hydroxide. We could, but we don't have to this time. All right. Oh, there. Gravimetric analysis. I know I gave at least 2 or 3 examples of those to try in the assignment somewhere. Next, let's wrap this up. You were introduced to neutralization reactions, I believe, in your chemistry, your first year courses. I'm briefly going to revisit some of that stuff. Just like precipitation reactions, just like metastasis reactions where nothing occurs, you don't get a precipitate. Acid-base reactions are essentially double replacement reactions, except they're a special case of double replacement reaction because they are dealing with acids and bases. Except now the products are always going to be a salt and water. But anyway, there's different types of acids and bases. Does anyone recall having this discussion before? You may or may not have. Looks like no one has. So this ought to be pretty interesting. The first theory on acids and bases is called the Arrhenius theory. This was developed a few hundred years ago. A few hundred years ago. Forget what his first name is. Aloysius or something like that. No, it's not that, but it's... Anyway, essentially what Arrhenius says, a substance is an acid in that it provides hydrogen ion. This is what you guys think of acids. This is what all you've been told that acids are up to this point. Provide hydrogen ions. How do you guys recognize a substance as an acid? Its formula starts with hydrogen, right? Okay. And that hydrogen dissociates. A base is a hydroxide ion provider or donor. There is hydroxide ion present, and it completely dissociates with some sort of metal. You guys know some strong bases. What are some strong bases? Any of the group 1A, the alkali metal hydroxides, and technically the group 2A, or the alkaline metal hydroxides. However, we keep referring to the fact that a couple of those, the smaller ones, aren't very soluble. Magnesium and the solubility increases as you go down the list. So you get down to strontium and barium hydroxide, those things are actually pretty soluble. Okay? But the extent to which calcium hydroxide does dissociate or does dissolve, it completely dissociates. You just can't get very much dissolved. Anyway, I don't know. Should I put examples up here? For the acids, are any of those strong? Gracie?
Hydrochloric.
And the
Nitric.
nitric. What is the other acid? Acetic acid, and it is a weak acid. But it still provides hydrogen ion, just not very much. And of course, we already mentioned some strong bases. All right. This is what you guys, you've really only known the Arrhenius theory of acid-base up to this point in your life. So now we're going to introduce, actually I introduced a couple days ago, the next one. Turns out two gentlemen essentially simultaneously came up with this theory, so they named it after both of them. Bronsted-Lowry theory of acids and bases. Acids, essentially the same thing as the Arrhenius theory, a substance that provides hydrogen ion. So according to Bronsted-Lowry, a substance that provides hydrogen ion is an acid. However, it differs from the Arrhenius because of this. It is clearly known. You guys, has anyone ever used litmus paper before? Litmus paper or pH paper? Okay. And litmus paper, basically all that does is tell you whether it is an acid or a base. It's kind of a yellowish colored paper. Has anyone used this before? If it turns red,
I'm going to say acid.
It is an acid. And if it turns blue, it's a base. That's all litmus paper does. It tells you whether it's acidic or whether it's basic. You can use pH paper to actually get an idea of how acidic or how basic, what the pH actually is. Has anyone used that before? Where you take a little strip of paper, you drop a little bit of a solution on it, you compare it to a color sequence, figure out approximately what the pH is, okay? Well, here's the deal. You guys all know what this is. Ammonia, okay? Well, when you have an ammonia solution and apply a little bit of that to a piece of litmus paper, it turns blue. Therefore, it is a base. Where's the hydroxide ion? There is no hydroxide. Well, we've already discussed this, but now we'll take it, do it again, and maybe it sinks in a little bit more. I'm trying to. I say something here, and I can't remember what it is. There we go. A Bronsted-Lowry base is a hydrogen ion acceptor. It doesn't provide hydroxide, but it accepts hydrogen ion. Where's it going to get that hydrogen ion? What's that?
Water.
Did you say water?
Water.
Water. Remember that hydrolysis thing? So, the example we can look at here is, and we already looked at this, and again, I'm going to write the water this way because I think it helps your brains see this. I mean, obviously, water's H2O, okay, but I think your brains see this process a little bit better here. We're just saying that ammonia is a Bronsted-Lowry base, which is a hydrogen ion acceptor. From where can it get some hydrogen ion? The water to form the ammonium ion and hydroxide ion. So another way we can say that instead of saying hydrogen ion acceptor is by saying it produces hydroxide ion through hydrolysis. You may want to add that comment there if you're people that like to look at your notes. I know some of you write the notes down and never see them again. Others of you actually read through those notes. Yes, I will. Another way of saying Bronsted-Lowry base is a hydrogen ion acceptor is saying that it is a hydroxide ion producer. Notice it's different than donating. It's producing hydroxide through hydrolysis. Hydroxide ion producer through the process of hydrolysis. Currently, this is the extent to which the AP is now testing you on acid-base theories. Arrhenius or Bronsted-Lowry. Acids are the same in both cases. The difference is Arrhenius only dealt with strong bases, where the Bronsted-Lowry also deals with weak bases. See the difference? Bronsted-Lowry explains weak bases. So as you go through the evolution of the theories, it's explaining more and more things that act as acids and bases. But now there's a reason why they do that. I am going to show you the third one that is no longer being tested anymore, but as you guys go off into your lives, you will be exposed to this if you continue to take more chemistry classes, so we can say that you heard it here first. I'll do it over here. You'll remember Mr. Lewis from Lewis, same guy, and you'll see how this applies here very, very shortly. An acid, give me a second here. Is an electron pair donor. Anyone want to take a stab as to what a base might be? Yep. I lied. Darn it. Why did you guys let me lie? The acid is the acceptor. Acid acceptor. Actually, that's not how I remember it. I just thought of that for the first time ever. There's another way I remember this. A base is an electron pair donor. Now what I'm going to do is use some substances that you might be a little bit familiar with, and this is how I remember which one's which, and write out a reaction. So, here's a good example. What is ammonia? Acid or a base? It's a base. We've already established that. So it doesn't matter what theory. It doesn't matter what theory you're talking about. An acid is always an acid, whichever the theory is. A base is always a base. What these theories do is they explain why more substances act as acids and bases. So let's take ammonia. Now what I'm going to do is write the formula for ammonia up here, but then I'm going to draw the Lewis structure. And if anyone remembers, there is an acceptable Lewis structure for ammonia. Remember, it has a lone pair of electrons. This is it's a base because it has an electron pair here. We're going to react this with a little boron trichloride. Now, you guys probably all drew Lewis structures for boron trichloride at some point in your earlier careers. I'll draw it once again. Is that an acceptable Lewis structure for boron trichloride?
No.
Why not?
It's gonna have.
Oh, the boron has to have an octet of electrons. Well, let's think this through. How many valence electrons does boron have?
5.
Valence.
Oh, 3.
3. It has 3. It's in group 3A. It has 3 valence electrons. How many valence electrons does chlorine have? 7. Yet there are 3 of them, so they are contributing how many valence electrons? 21. And the boron, as we said earlier, has 3 for a total of 24 valence electrons available in the system. Have I utilized all 24 of those valence electrons?
To make it 4.
I have. Yet, the boron still doesn't seem to have an octet. Is that okay?
I don't like it, but
Why? No. I actually introduced this to all of you that I had back when you were taking chemistry. Yes? Oh, you're going to different thing. There's 2 exceptions. That's the other one. There you go. Boron and beryllium are allowed to be electron deficient. The third period or heavier are allowed to have an expanded octet by having more than 8. You had part. You're close. Anyway, does anyone vaguely remember the boron-beryllium thing now, electron deficiency? Okay, so there you go. We're going to cover it later in class, or in the course, but you can write it down if you want. So anyway, do you see how this fits into the Lewis acid-base theory? Ammonia, we already know, is a base for all the reasons we've talked about. It's still a base because it is now a electron pair donor, whereas the boron can be an electron pair acceptor to form that compound.
Ooh, I don't like that. Why isn't it?
Yes.
Why wasn't ammonia? Ammonia. Why wasn't ammonia for?
Ammonium.
Ammonium. Sorry.
Where's the other hydrogen?
I thought this was water. It's not.
Could be. Anyway, you will not any longer have to worry about this on the AP exam. I just wanted to show you. They used to make you know this stuff. They currently don't.
So are you gonna test on this?
Nope. I'm just showing it to you. Like I said, you heard it here first.
Wait, the third one?
The Lewis acid-base theory you are not responsible for, as of a minute and 38 seconds ago. Yes? Yes, precisely, because it accepted an electron pair. It is. If you applied some litmus paper to it, it would could behave as an acid under certain conditions. Put it this way, it reacts with a base. Okay, with that being said, let's do a little neutralization stoichiometry here. As I said earlier, the products of a neutralization reaction are typically a soluble salt and water. First example. Well, can I let you guys go on this?
Let me read it. Hang on.
I think I can. Ready, set, go. Should have seen the look on about 3 people's faces. 2 of them were Chelsea. She's like, really? You want us to do this? Okay. What is, Gracie, what is your evidence that those are mixed in water?
I don't think they're mixed. Wait, yes they are.
How do you know this?
I know it.
No, that has nothing to do with it. You can measure milliliters of ethanol, gasoline, acetone, none of which have water in them. Look at the other thing. What does the big italicized capital M mean? Molarity. What is that referring to? In an aqueous solution. I had in my possession at one point during... Yes.
What? Judy!
Why would you do... What?
I didn't do that.
Thank you, Judy.
I just know it's over it.
Thank you.
I'm sorry. I just was saying.
I was taking it from him, and I was going to say, if you give me money for the rest of the year, I'll tell you where it is. And that spoiled my plan. And now I am sad.
Gracie, you could give me a lifetime supply of Diet Dr. Pepper, and that still would not get you an A. You earning an A, I'd be all for that.
A lifetime supply of something that you can make money off of.
I don't care about money. I don't care about money. You've seen my shoes.
They're not fashionable.
But they're comfortable, and they didn't cost me much money.
I should buy you a pair of, like, Skechers shape up for Christmas. What size are you in shoe? I'm going to buy you Skechers shape up.
Oh, shoot, wrong shoes. I thought I had my Skechers on. My brown ones are Skechers.
Or the Skechers shape up.
I have no idea what that means.
I want Skechers shape up for him.
There's a shoes that like curve up at the end that help you lose weight.
That what?
You can't help it. Skechers shape up.
You mean like elf?
They're like the ones that like
Oh, I've seen that.
up in like a circle. They're supposed to like help you lose.
They don't, you know what helps you lose weight? Walking.
You've seen your shoes.
Yeah, exactly.
I know. I'm just saying supposedly.
Do you have a balanced chemical equation written? Do you have one-to-one stoichiometry? Awesome. What are your products? Yep, a soluble salt, in this case potassium nitrate.
Does the water precipitate? That's one question. Like, I feel like I don't know.
Water is water. If it's in water, then it's the same thing. It doesn't do anything.
All knowledge that you have used before. Everything up here. Well, one possible thing.
Do you need that, please?
Oh, well, yeah. What? Why? Yeah, why do you say that? No, let's hear it. I don't know. Is it? How do you know? Excellent. So how many moles of nitric? Just be quiet. Just stop. How many moles of nitric acid? 0.007. Great. How many moles of potassium hydroxide? 0.01696. Therefore, which is it a 1-to-1 stoichiometry? Okay. Is it? Yeah. Okay. It is. Okay. So anyway, which one has the least amount? Therefore, it's a limiting reactant. How many moles of the nitric did we have? 0.007. That is incorrect. That's 0.007. And how about the potassium hydroxide? 0.0169. Is this correct? Yes. It is. Okay, so it is a 1 to, and now I'm telling you this right now, on the AP exam, you can get away with this. It is a 1, by saying this, instead of doing the math, you can say, if you've calculated the moles of these things, they would need to see evidence of that, okay? But you can say, without having to do a stoichiometry problem, a setup, all that stuff, due to the 1-to-1 stoichiometry, there is less nitric acid than there is potassium hydroxide, therefore this is a limiting reactant. You need to provide some evidence of a thought process that led you to believe that one was limiting. You guys see where I'm going with that? Okay. You can phrase it. No, I'm not going to repeat it. I know. But what I don't want you to do is have to memorize a sentence. Okay. I was saying that due to this 1-to-1 stoichiometry, it's clear that this is a limiting reactant because this has less than this. You can also do it if it were 2-to-1 stoichiometry, and you could say it's clearly not double the amount. Okay, anyway, moving on. so this is our limiting reactant. Oh, by the way, here, you can have this to keep track.
I do.
Okay. So now what are we looking for? We're looking for the volume of water. So we start with our, I'm just going to go from here. Do you see what I did there?
Yes.
You can also get away with that. Why? Because it's a one-to-one stoichiometry. What I'm trying to do is show you some ways to get through some things faster and still provide enough information for the graders, for the readers, to give you some credit. Okay? But now we have a problem. We're looking for the volume of water. Does anyone happen to know the molarity of water? Yeah, I don't either.
I don't know. Okay, I have an idea.
Go ahead.
We could use the M1, P1.
No, we cannot. Joe, we can find the grams of water, and then the density of water, which we all know is 1 gram per milliliter. So the volume, or sorry about that, the mass is equivalent to the volume. And Joe, did you do that?
I did, but I'm doing like 126.14 milliliters,
Which is precisely wrong.
yeah, so I was thinking because it's,
I'm not sure. Listen, Joe, I'm not sure. Joe, you got 126.
I got.
No. Did you touch your? You got what?
I thought it was in liters still.
Okay.
0.126.
There we go. I'm just trying to help you out here, okay? You do have really, really good thought processes a lot of times. And there's other times you just kind of forget to think. Isn't that weird that you do both at the same time? Yes.
When you did the 1 milliliter for like over 1 gram, that's
That's
like
the density.
like
Yeah, that's the density, but except it's inverted
yes.
as a conversion factor.
1 gram of water equals 1 milliliter water, which equals 1 centimeter cubed of water.
Yes.
Yes.
Look, more knowledge. Okay, there's not a single thing up here that you guys did not know how to do. What we did have to do is pull some of it from places that we haven't visited for a little while. That's okay. The next piece, it's very possible that I'm almost guaranteeing that my former students do not know this. It's possible that other of you may have done this. What's the other part of the question? Is it acidic or basic?
Water? I'm going to say it's basic.
Why would it be basic?
Oh, it says water. I'm like, wait, that's the question? Is it about water?
No. Is the solution as it exists currently acidic or basic?
Oh, it's
Why, Joe?
because there's leftover potassium.
Because the excess reactant is the potassium hydroxide, which is a base. Here's the next question. Is everyone, first of all, is everyone okay with that?
Yeah. Let me write it. Because excess reactant is...
The excess reactant, now, if the limiting reactant had been the potassium hydroxide, then the resulting solution would have been acidic because we had excess acid. You guys get this now, right? See, that's a very fair question. This next one is kind of fair. Did anyone remember learning to calculate pHs? I don't know if we got there. We did not get there because we did the little organic unit instead. For me, at that time, because I knew we were going to do acid bases in this class, I was more concerned that we get the organic in.
I think Mr. Cosley showed us something about it one time.
Possibly. She may have shown you. Does anyone else? Let me see. Who am I not? Anthony, do you remember calculating pHs? Oh. Okay. Well, you should have in Homan's class a little bit. You may not have gotten. Okay. Well, anyway, here is the equation to calculate pH. Oh, logs are easy. You press a little button, it says log.
No, but my computer's broken. Oh, no.
Oh, then do it in your head. Oh, easy. What are you going to do them later in the year in the head?
No, you're lying. Where's that?
-4.
Nope. Yes, -4.
Wait. Is it just the power?
Yes!
What? See, that's annoying. Yeah, because normally it's
The hydrogen ion?
Think it through.
How can I find the log of the
Just give me one significant figure. You're trying to decide which way to go. Are you trying to decide which way to go? Okay. Well. Negative 3.8 something.
It's the lemon.
When we do the whole unit, you'll find out you can do that too. Hold on. Now, the problem is with this equation, this finds pH for us, but we have no hydrogen ion left because it was the limiting reactant. However, anyone want to take a stab here?
Oh, I remember that.
Anyone? What? No. The hydroxide ion. And you can go one of two routes from here. Yeah, I think you did too. I didn't get to it. I did other thing. What I did is I did something else.
Why would you organic chemistry?
You'll find out.
Does the H and P stand for hydrogen?
Yes.
I didn't realize that until the show either.
I was about to say, I'm like, there's no way everybody knew that.
I didn't know that.
Come on, just somebody needs to know that.
It's an operator. It means negative log of. Seriously. You can put, here, you can do this. Joe's going to like this one.
Wow, we definitely did this. I learned something. Alright. I have one organic chemistry. You learn something every day, whether it's bean juice, or hydrogen. Coffee and other more hydrogen. We just put it in. Or safety
Pea cabin?
Oh my God, dude. Shut up.
See, I told you Joe would like that one. Yes. Time out, I'm not done yet. I can't hear what you're saying. You may have had a real question. What is that?
My brain's going like
Stop.
right now. So, how do we find like the log of hydroxide? Like, how do we never look at
Oh, time out. Listen. No. Where I'm going with this. This, even though it's brand new to probably 90% of you, you've never seen it before, I'm hoping you recognize this is a really easily done thing. You guys know what the brackets mean. Molarity, concentration of the individual component that we're talking about. Hold on, keep it going, okay? So obviously you take the negative log of that, and boom, you have your pH. Okay, that's something you press 2 buttons on your calculator, you're done. Okay, this you don't know what it means yet, but clearly you could deal with this equation. Okay, there's not a mathematical thing up here that you would have any difficulty with. But here's the real question. You actually had a real question there. How am I supposed to know how much hydroxide ion is there?
Isn't it like the problem that we did the other day?
It's like the 2 problems that we did the other day. Ready, set, go.
I'm sorry. I have to find it.
I'm sorry about that. No. But you've practiced finding each of them. This time you're finding the hard one. Yes. You can do whatever you want, yeah. No. This will be the final act for Chapter 4, Part 2, which we're taking about 8 different things that we've learned this year and thrown into one question. This could easily be a real AP extended response. Part A, Part B, Part C, Part D. What I'm asking, what they're supposed to be doing, and it's in that packet, is find the pH of the resulting solution. So the first part of the question was, is it going to be acidic or basic? Because the base is the excess reactant, there's a little bit of hydroxide ion left over, so it's going to be basic. I'm asking them to find out exactly what the pH actually is. Okay. Ask somebody else. Okay. Don't ask me, ask somebody else. Please ask somebody else. People, this is easy. It's a one-to-one stoichiometry. This is incredibly easy. And sometimes you do that. We've got to, and you've heard me probably say this before, you have to determine what's hard and what's easy. Let the easy stuff be easy. Just to speed the process up a little bit, how many moles of hydroxide ion are remaining? Say this again? No. 996? Yes. That's the moles, though. What is the volume? 0.08. Okay, look. We have 0.007 moles of HCl, or HNO3. That's the limiting reactant. Since it's a one-to-one stoichiometry, how much of this is going to get used up? No, it's a little bit more than that. Well, okay, but what are you going to do? You're going to subtract. The remaining is the moles of hydroxide ion. However, that's just the moles of hydroxide ion. In order to use this, we need to have the concentration, so we're going to have to divide by what? The volume that the hydroxide ion is existing in, which is what? 81 milliliters, or 0.081 liters. Yeah. Is that it? 0.0099? Thinking it might be that. Moles.
Okay, yeah.
Now, where did I get that, Chelsea? Yeah, it's the 2 volumes added together and converted to liters. I gotcha. And now, does anybody, what is the concentration? 0.12. So it's 0.122 molar. Then, and that's hydroxide ion. Yes? Which we're then going to take over here and plug into this handy-dandy little thing. So it is going to be, I'll tell you this here in a second, that's down there, 0.7 something? 0.8? What is it? Oh, okay, so I went too far. But it's going to be less than 1 because it's a little bit more, okay. So anyway, 0.9 something you say? 0.993? 913? Okay. Oh, that is a result. Oh, my bad. That was dumb of me. You're right. Hold on. So, negative log of 0.122 equals 0.913. There's our POH. But I'm asking for what is the pH, so we're going to subtract that from 14. We're going to get a 13.1-ish. Yeah, probably. I've kind of quit keeping track. Is that basic? A pH of 13? I know. A pH of 13 is extremely basic. Okay. 7's neutral. Closer to 0 is acidic. Closer to 14 is basic. We will cover... Well, yeah, it does because it's negative log. It makes perfect sense if you think this all the way through. But anyway, where I'm going with this is we do not get your panties in a bunch about anything below that line. That is the entirety of chapter 4 or 16. Yes.
But why is chapter 16, or like, why is it so hard if it's so basic?
Somebody please grab a large, heavy object and throw it at Joe's head.
Okay.